Now for the real data, we've already loaded the JSON dataset. And this is just, if you recall, the data processing we did before. We create a cross tab. We then pick Tennessee Warbler as one column from that wide format table. And then here, again, create our data set that is going to be the input for the multinomial model. So what is going to be interesting here is this y, d, and x. And again, this d is not density. This is just our protocol. So head of y looks like this. So again, this is one species, multiple stations. CL 10.10.2, 10.10.6, 10.10.8. These are the stations. And then we have the counts, the total counts that we used before, now broken down into these intervals. In the first 3 minutes, we detected 4 and then nothing. Here we detected 2, then nothing, and so on. Now head of D, this is where we have these end times. And why I like this specification is that you can have each row referring to a different protocol. So you might have 3, 5, 10, 1, 2, 3. So if you have multiple protocols, this is just a nice way of putting everything together if you know the end times. So what happens when you have 3 intervals versus 5 intervals versus 2? Then you just go as wide as you want, and you put maybe 3, 5, 10 here, 5, 10, and NA. So whatever was not used, you just put an NA, and then you also put an NA here in Y so that there is no count coming from a non-existent interval. And then the column names are really not used. So it's more the times if you kind of mix and match different protocols. And I'm not going to spend a lot of time today on this, just putting it out there that one of the reasons we did this estimation this way is because we wanted to combine different data sets. And this is a nice way of allowing that flexibility. So now the head of X, and by head, I mean the first 6 rows. I'm just having these 2 columns because this is what we are going to use. Day, that is the ordinal day of year divided by 365. So we get a number between 0 and 1. TSSR, that means times since sunrise. So if you calculate time of day as a 0 to 1 number, so time of day in hours divided by 24, now you have this number, and you also know when the time sun rose. They can calculate, was it like 1 hour before sunrise, 1 hour after sunrise? So when this is negative, summary X, that means it happened before the local sunrise. When it's positive, that means it happened like 5 hours after sunrise or so. So this max. So this is the data what we are going to use to fit a model when we don't assume anymore that this phi, this rate is constant. It might change over time. Here's an example of what I was talking about before, like the different protocols, 3 to 5 to 10, 1 through 3, 4, 5, or 0 to 4, 4 to 8. The rest should be filled in with NAs, and the corresponding counts should have the same patterns with respect to NA. So before we go for a short break, let's just see how we can fit the same model as we did before for the simulated data, but now we are using Y and D that's coming from the real data set, the JOSM data collected in Alberta. I'm going to use capital M as model, E that stands for exponential, and null that this is an intercept-only model. So we run this. We get a nice summary. You can see the call, removal sampling, homogeneous singing rate, conditional and maximum likelihood estimates, log phi is our intercept, and we get minus 0.85. Standard error p-value. As we talked, p-value has no meaning here. And some log likelihood and BIC values if you compare across different models, which we will do after the break. And so the only thing I want to explain the singing rate. Maybe that's how I can express it most colloquially. So,
sorry,
yes.
Could you repeat that? I feel like, at least on my computer, you froze for a little bit right when you said the one thing I want to take
yes.
home for this.
I also got a notification that my internet is unstable, so let me just repeat it. So what we estimate here is the log of phi. And phi was the rate before, right? When we were doing the simulation and time to first detection and the exponential distribution and the binned data, the cumulative density, we had this single parameter called phi, which was 0.5. And that was the number of events happening per unit time. And our unit of time is a minute. So 0.5 per minute was our singing rate. And because this cannot be a negative number, this is why we often, in a statistical model, we take phi and estimate the log of it, because the log of phi can be anything between minus and plus infinity. So our models are not going to require any kind of babysitting, that if that's negative, then do nothing. If it's positive, go on. This way is just whatever number, what we get, then we exponentiate back. So what I do here, I take the coefficient of ME naught and exponentiate. And that is going to be our estimate for phi. Oh, that's already printed here, 0.425. So this is our estimate of the singing rate for Tennessee warbler based on the JOSON data. And finally, before the break, this is what that looks like. So we have the binned data, and I just divide it by the max, like the sum of y, because that's just how we can easily put these two things together. So we have the binned data, the proportion of the counts, and then this is the fitted curve with phi equals to 0.42. So this is how the data and our estimate relate to each other. And next, we are going to see how things vary with time, and then play with B-sims, and we are going to do some simulation to see how violating the assumptions is going to be distorting our estimates. So the next chapter is going to be about non-constant phi. And here I'm just going to go real quick so that we have some time to play with the simulation. So time varying conventional removal models. This is a lot in this statement. Time varying means that phi is not constant, but it varies with time. And conventional is going to be just this exponential model that we've talked about. And it has this intercept at 0. And depending on the rate, it goes up fast or goes up slower. And we are going to see there are other, which I call non-conventional, there the intercept might be something else too. So let's just see how to fit these. Type equal rim, that means removal. That's just the shorthand. And we'll have the same function fitting distance sampling as well, because the multinomial model is very similar, but we express probabilities somewhat differently, but we can still use everything else inside. So if I say type equals this, then I'm thinking y is now distance sampling data. So this is something to keep in mind when you're using C-multi. You need to specify what model you are fitting to y and d. And now on the right-hand side, you see day and TSSR, and we have these two models as ME1, ME2. Once the estimation is complete, you can do model selection. So here we have this MEAIC object, which is just based on that AIC. ME1 is the best, so that's what I stored in ME best, and that's the summary you can see here. We have an intercept and the day related slope term for log phi. So you can think about this. If you have to predict phi for any day, you would have that standardized, like the number of the day, ordinal day, divided by 365 times the slope plus the intercept. Now you take this value and exponentiate. This is how you will predict phi for any given day. So you can take these estimates and make a prediction based on the best model. And this is just some code to visualize how phi varies with day. So you can see here now, probability of availability is calculated based on P, or yes, phi. So if we had, for example, this 0.5 value for phi, then the probability would be 1 minus e to the power minus t times phi. And by t, I mean, what is that total duration? Is it 3 minutes or 10 minutes that you're counting towards? Because that's what this cumulative probability is going to be. If you wait longer, 3 minutes, 5 minutes, 10 minutes, this probability is going to be different, even though phi is the same. So if you want a probability over 3 minutes, that would be 1 minus e to the power minus 3 times phi, and phi is something that we estimate from the removal model. If I say 5 minutes, that's 0.91. If I say 10 minutes, that's very close to 1. So this is how, under value of phi, you have the cumulative density function that you can use to calculate probability of availability, which was P in our QPAD notation, if you recall. So now, if instead of we look at how phi varies over time, we look at how availability varies over time, we see this relationship, and the coloring, you see early in the season, you see red, later in the season, you see blue, in between it's yellow. The same rainbow colors can be seen here, and that just means phi is somewhat higher, so the CDF is on top here early in the season, and then it goes down. There's not a lot of difference because this is a relatively narrow time window, but still, this is how you can think about phi, and as a result, availability being a function of a covariate. Any questions regarding this one? When it's a function of time or day, how these estimates are then translated into the P probability of availability. We fall back to the exponential model. We know the cumulative density, how that should be parameterized based on phi, and this is how we calculate P.